This is my reassessment for Standard 9, which is Chapter 11. In this problem, you're sitting on a rotating stool and you're holding barbells in both of your hands while your arms are stretched out. And during that time, it takes you 2 seconds to make a full circle on the stool. But when you move your arms in and the barbell's closer to you, it makes you go faster, and we're trying to find out how long it will take us to make a complete circle then. In this problem, we're not given specific values for anything, so I'm making my own assumptions here. So for the mass of each of the barbell is 5 kilograms. The first moment of inertia I'm saying is 1,000 kilograms meters squared. R1, which is when your arms are completely out, and this is the distance from the axis about which you're rotating, which here I'm assuming that goes through like the center of the stool and the center of the person to either one of the arms, the barbell lengths. And then R2 is when you pull your arms in and the barbells are closer, and that's that distance. Here we know that the total angular momentum for our system, which in this case I'm saying is the barbells in your hand and the rotating stool, and the total angular momentum of that is the moment of inertia times the angular speed, and here we are assuming it's constant. And first we need to know what the angular speed is when your arms are fully extended, and so we're going to start with omega is equal to 2 pi over t1, because that is our period here, and plugging in our t1, which is 2 seconds, we get 3.14 radians per second. Now we need to find the moment of inertia for when our arms are close together and the barbells are closer to our body. And the formula we'll be using is I2 is equal to I1 minus 2mr1 squared minus 2mr2 squared. Here we can take out the 2 times our mass, and we get I minus 2m times r1 squared minus r2 squared. So now we're going to plug in the numbers that we have assumed, which for I1 is 1,000 kilograms meters squared minus 2 times the 5 kilograms, 2 because there are 2 weights there, times 8 meters squared minus 1 meter squared, because that's the change in the barbell distance from the center of the rotating axis. That gives us 1,000 kilograms meters squared minus 630 kilograms meters squared, and that is equal to 370 kilograms meters squared. Because we know that I1 omega 1 is equal to I2 omega 2, we can rearrange this algebraically to find, oh, I have that written down wrong, but it's to find omega 2 and not the moment of inertia 2, because we have already found that. So here it would be omega 2 is equal to I1 omega 1 divided by I2, which I have correct down at the bottom here. And plugging in our numbers and the moment of inertia for our arms closer together that we just found, we get 1,000 kilograms meters squared times 3.14 radians per second over 370 kilograms meters squared. and that gives us 8.5 radians per second. So now we can use this to figure out the time it took for us to make a complete turn with our arms closer together and the barbells closer to our body. And so we plug that into our period equation, which is 2 pi over omega 2, and that's 2 pi over 8.5 radians per second, and that gives us 0.74 seconds, which is significantly less than the 2 seconds it took for us to make the complete turn with our arms further out.